So, just to summarize everything we have looked at, the MOSFET operates in two regions. Okay. So, we have so far we have only considered two regions, which is if I were to plot the IDS versus VGS, we have till the threshold voltage we do not know what is going on, but after the threshold voltage, depending on the value of the VDS chosen, the MOSFET can either be in linear mode of operation or it can enter saturation mode of operation. Okay. So, if I once you pick a certain VDS, okay, so let us say VDS is now fixed for values of VDS less than VGS minus VT. Okay. So, let us say that, which implies that in this region. Okay. So, this is the region where let us say VDS has got the possibility of being less than VGS minus VT. The MOSFET will be in linear mode of operation, and in this region the MOSFET will be in saturation mode of operation. But so far we have not discussed what happens to the MOSFET below threshold voltage. Now, so while discussing the current voltage characteristics, we used a very simple figure. Okay. It was just done so that the current voltage characteristic, you could sort of imagine what is going on while deriving the first order model for the current voltage characteristics of the MOSFET. But here is a more accurate picture of the situation. So, you have your gate metal, you have your source, I have grounded the source, you have the body, in this case the body is grounded. So, the body to source voltage is 0, and you have a VD, a drain voltage which is being applied. So, you have a certain drain to source voltage that is greater than 0, and you have a gate voltage, that is VGS is greater than the flat band voltage, or in this case since the channel is already formed, we will say it is greater than the threshold voltage. Now, when you say, when we made this initial approximation, that is in the case of linear operation, we said that VDS is very small. It does exist, but it is very, very small. Okay. And as a consequence of that, we found that you do have an inversion layer, but the inversion layer has got almost the same concentration per unit area throughout the region from source to drain. But what we did not show in the previous picture was also the depletion region. So, if you remember the MOS capacitor, you first deplete the semiconductor, and it is only after the semiconductor is depleted that you form the inversion layer. So, you have two regions here, which is the inversion and the depletion layer, and in the previous pictures this is not made very obvious. So, I am trying to make this quite clear here. And if you remember the band bending, so if I were to take a cross section like this, okay, so this is through the MOS capacitor. So, you have your gate metal. So, let us say we start from point A and you head to point B, and we are going to draw the band bending along this cut line. Okay. So, at A you have your gate metal which has got a certain work function. Okay. So, that is the work function of the gate metal, and we have applied positive voltage to this device by this time. Since you have a P type body, although it is shown in the same color, you have a P type bulk. So, you have applied a positive voltage to this, which means that you have suppressed the work function, you suppress the Fermi level of the metal, and then you have the insulator. So, from this point, so let us say A dash to A double dash, let us say. So, this is your A, that is your A dash, and from A dash to A double dash we have the region of the insulator. Okay. So, that is the insulator, and it is only after the insulator that you have your semiconductor, and right now your semiconductor is in has got significant band bending, with the Fermi level located here, which is above EFM, and you have the intrinsic Fermi level bending this way, and this region here, the channel region, is essentially the electrons that have accumulated here. So, that is the channel region which is shown in blue in the figure, and this grey shaded region is the depletion region. So, it is basically all the acceptor ions that were all exposed and are compensating for the charge applied on the gate metal along with the free electrons. So, you have free electrons and the depletion layer exposed ions compensating for the charge. So, this is the picture of what is there along this cut line. Now, if we were to increase the VDS, so we do not have a VDS that is very small, that means you cannot ignore the VDS anymore, but you increase the VDS. So, if you increase the VDS significantly, if VDS goes up significantly, you see this PN junction here, this PN junction becomes more reverse biased because your bulk, this P can be said to be at ground. So, you have a PN junction diode where that is the N side, that is the P side, that is the N plus that is contributing to your drain region, and that is the body or the bulk of the semiconductor. When my VDS goes very large, so this is my VDS and that is my VBS, which is now connected to 0. So, my VBS is 0 because my body is at ground. So, if this gate, if the drain voltage goes to be goes up, you increase the reverse bias on the PN junction, and therefore, this depletion layer around the drain region should increase significantly. Okay, I probably exaggerated it here, but you will not have such nice sharp lines, you will have a region that is much more gentle and gradual like that. And near the source side, since the PN junction has got 0 voltage across it, it will have the same depletion layer. For all practical purposes, it will have the same depletion width as one would expect in equilibrium, okay, with the exception that you have an active gate field right now. So, you will find that the depletion layer in this region is going to be much smaller as compared to the depletion layer thickness near the drain side. And also we also saw that the channel potential, so the channel potential varies as you go from drain to source, and this channel potential also affects the free carrier concentration, which is the inversion layer charge, and therefore one would find that the inversion layer charge actually decreases as one heads towards the drain side, and this leads to the pinch off and therefore your saturation mode characteristics. So, in our models so far, we never took into account this variation in the depletion layer thickness. And why is that important? So, if you recollect our models, okay, we always said that Qn, which is the number of electrons, or let us say the number of electrons at the interface per unit volume, was equal to your Cox into VGS minus VT minus the channel potential, and we used this picture to accomplish that equation, right, because here the depletion layer is not varying too much because our VDS is very small. But then while talking about saturation mode operation, we just continued using the same equation and substituted VGS minus VT for VDS after giving some qualitative analysis. Okay, so can we quantify these bits a little better? Okay, so that's the point of the next few slides. So we said that Qn is equal to Cox into VGS minus VT minus Vc. Okay, but the problem in assuming that XD is constant everywhere is related to the threshold voltage. Okay. Why is it related to the threshold voltage? What is the threshold voltage? The threshold voltage has got 3 milestones. Okay, the threshold voltage, for accomplishing the threshold voltage, you need to first get to flat band condition. You need to put enough charge in the gate so that you are at flat band. Then you need to deplete the semiconductor. Okay, so in our case the depletion charge is negative, so I will just use a negative sign. And after that we need to increase the surface potential till the surface potential matches 2 times phi f, where phi f depends upon the doping concentration of the p type bulk. So, VFB so far is only related to the metal semiconductor work function difference. That really does not matter, it really does not care as to whether the depletion width is increasing as we approach the drain side or not. Similarly, phi f only depends upon the dopant concentration Na, right. That too is not dependent on the thickness of the depletion region, but Q depletion obviously should depend upon the thickness of the depletion region. And what is Q depletion? It is a depletion charge per unit area, and that is going to be minus Q Na into XD. So, in all our assumptions so far, we have ignored this fact, okay, and this is something that we will address in these lectures. Now, that is one fine tuning to the model. The second problem, okay, the second deficit in the models that we have developed is as to what happens when VGS is less than VT. Okay. We said, okay, when VGS is greater than VT, you have the linear mode of operation, and then you have the pinch off and therefore the saturation mode of operation. And so far for VGS below VT, the current was said to be 0, okay, and it was here somewhere that the characteristics started off. So, if you plot VGS versus IDS, the current is 0 till a certain point, and then the characteristics start off beyond that point. Okay. Now, that is rarely the case. Okay. You do not have electrons sitting there at a traffic stop and waiting for VGS to become greater than VT. The physics is much more smoother, and it is much more natural, much more gradual, I should say. And when VGS is greater than the flat band voltage, but less than the threshold voltage, you do have something called as weak inversion. And what is weak inversion? Weak inversion means that the band bending at the semiconductor insulator interface looks like this. You have let us say this is the Fermi level of the semiconductor, and the intrinsic Fermi level does start bending a little, and that is your depletion region, and as it bends a little more, your EI minus EF or EF minus EI near the interface becomes greater than 0, which means that the EI has gone below EF, and as you keep increasing the gate voltage, it continues going below EF till the point where the bending is so much that EI minus EF, which is becomes equal to phi f, or the surface potential becomes equal to 2 phi f, which is when we say that we have hit threshold. But all these regions, okay, wherein phi s is greater than phi f but less than 2 phi f, okay, all these regions are said to be weak inversion, which means that electrons are encouraged to appear at the surface, okay, starting from well before even when phi s is less than phi f, electrons do start appearing at the surface, okay, but this is the concentration is still not large enough for us to say that the device is completely turned on. So, that is the region which we have completely blanked out on in our model. So, we are also going to correct for that aspect. So, that region is something called as the sub threshold region. So, we will address two topics now. One is the correction to what happens at VGS less than VT, and the second is taking into account this variation in XD to correct for the threshold voltage. So, when the VGS is less than VT but greater than the flat band voltage, we are in weak inversion, okay, or it is called as the sub threshold region of operation. Now, as long as you have a VDS, you do have a current, okay, but we need to be careful about how we model this current. Now, in the case of inversion, we had a complete electron channel connecting the source to the drain, right. It was like one long resistor that was connecting source to the drain, and therefore, the drain to source voltage was sort of divided, it was spread across this resistor. So, as you moved from the drain to source, every electron felt the field of the drain voltage, field of VDS, and therefore, we could model the current as a drift current. Okay. But in the case of weak inversion, what is expected is you have a certain VGS, okay, and if you look at this PN junction, okay, so these are, if you let's draw a cut line this way, okay. So, what do we have? We have an N type, you have a P type, though it's shown in the same color. So, this is a mistake here, it should have been shown with a different color. So, you have your N doped source and N doped drain, and you have a PN junction that looks like that, right. So, that is the P region, that is the N region, and this is the depletion width there, that is the depletion width there, and this is a PN junction. So, the moment we apply a VGS, what happens is we try to suppress this barrier, and therefore, the electrons are encouraged to try and occupy the region between the insulator and semiconductor from the source. Now, while performing the analysis under full or strong inversion, we assume that many electrons had already come in and they have already formed a channel. But under weak inversion, you can say that the VGS is so small that we cannot make that assumption anymore. So, you do have some suppression near the source side. You have more suppression of the barrier near the source side and lesser near the drain side. So, let us say that, and therefore, you do have a lot of carriers injected near the source, okay, but they are still not large enough for them to form a continuous channel, which means that if you look at this depletion region, this PN junction diode, the field here due to this PN junction diode is completely dropped across this depletion region, okay. And therefore, these electrons really cannot feel the drain to source field till they have reached this depletion boundary, okay. So, the electrons need to migrate from here to here into this depletion boundary before they actually start drifting towards the drain. So, therefore, what do you think would be the mechanism by which the electrons injected here could move to the other side? Okay, the answer has to be diffusion, right. So, you have electrons being injected near the source and not so many being injected near the drain, okay. So, you have a concentration gradient in the electrons, and these electrons do not feel the drain to source field till they reach this depletion edge, and therefore, these electrons are now their movement or their flux is governed completely by their concentration gradient, and therefore, the mechanism of transport is diffusion. So, in subthreshold region, okay, we cannot use a drift equation to model electrons, but rather we must use the diffusion component. Okay, so, this is how we go about it. Just a very quick estimate is as follows, right. So, the carrier count will vary exponentially with the surface potential, okay, and as we move from the source to the drain, we find that the carrier count increases, okay. So, decreases. So, let us say n, or the number of electrons per unit volume near the source is n0, okay. So, we have defined the source and the drain like this, and we say that this is y equal to 0 and that is y equal to L, and at y equal to 0 we are defining the carrier concentration as n0, and at y equal to L we define the carrier concentration as n equal to n of L. So, the diffusion current is Q times whatever the area of cross section is, okay, into dn, which is the diffusion coefficient, so which is approximately kT mu by q, that is the diffusion coefficient, and the concentration, the derivative of n with respect to y, which brings out the concentration gradient. So this is our diffusion current. And what is A here? A is whatever thickness you want to associate. So the last time while performing the analysis on inversion, we said that let us treat all the electrons like a particle, and this sheet of electron charge had a thickness of h. Okay. Now we never defined h, okay, and because h cancelled off, but here let us retain it and we will try to get an approximate estimate of what h is. So this will constitute the area of cross section, which is the channel width into this thickness h. Okay. And instead of dn by dy, instead of me getting a estimate, a perfect estimate which relates to the channel potential of what n is with respect to y, what we will do is we will make a big approximation here and say that dn by dy is simply n of 0 minus n of L divided by L. So which means is the carrier concentration near the source minus the carrier concentration near the drain divided by L. Okay. Big estimate, it is a big approximation, but nevertheless it is very useful to get a quick answer. So we say that this is our dn by dy. Okay, and therefore we will now go ahead and compute what dn by dy is. So near the source side, this is the expected carrier concentration. You have NPO, which is the number of electrons in the p type bulk at equilibrium, into e to the power q phi s by kT, which is like the forward bias voltage applied to your diode, the source and bulk diode. And near the drain side, okay, or at any other region, you would have n of say y equal to NPO e to the power q phi s minus Vc of kT. Okay, there is no channel here, but it is the potential gradient as you go from source to drain. And near the drain side, this would simply be VDS. Okay, so at n equal to L, at y equal to L, n of L is simply NPO into exponential of q phi s minus VDS by kT. Okay. And what is this h? The channel thickness, right. So a good estimate for h, okay, so you should remember that the electrons form a very thin channel, it is basically just a sheet of charge. Okay, it is not very thick. In fact, if you, although this is all, we are not doing this as part of this course, if you look at the profile of the conduction band here, you have all the electrons sitting here, and these electrons all have their own wave function, and essentially these electrons are sitting inside a triangular box of some sorts, right. So it is, if I just approximate everything like this, if I draw my conduction band diagram like this, and if I say that this is the insulator, you have electrons that have a certain wave function that are sitting inside this box. And what is the potential profile? The potential profile on the left side you could say is a finite potential barrier because of the insulator, and on the right side is a triangular potential barrier, and the electrons also experience significant electrostatic interaction between each other, and therefore that also gets involved into the potential term. So it is a complex situation right here, but it is, you could expect the electron wave function to be, to have a non-zero, you could expect the electron wave function to penetrate these barriers, and therefore the electrons have a non-zero probability of occupying the regions in the insulator, etc., etc. But what we are doing here is we just want to understand what this thickness is. Okay, we want to understand, get an estimate for the thickness because we want an approximate answer to what our subthreshold current is. So, what is an estimate of this thickness? The estimate of this thickness is the estimate of the penetration depth of the electric field, right. So, you have your band bending in the semiconductor because of the applied gate. Okay, so you have the insulator there and you have, due to the applied gate voltage, you have band bending in the semiconductor, and beyond a certain point xd our bands become flat, but once the electrons appear at the interface, what is Poisson's equation? Poisson's equation now becomes dE by dx is equal to the electron charge, right. So, it is the electron charge by epsilon plus the acceptor ion. So, you also have the acceptor ion charge. So, this is the Poisson's equation that we need to solve, and this is a function of the potential. So, we have already looked at this case when we looked at the ohmic metal semiconductor contacts. Okay, if you remember the ohmic metal semiconductor junction, of course, there probably we did not have we used N type semiconductor in any analysis, but nevertheless the idea is the same, and you do have an electron charge which is dependent on the potential, and therefore, you need to use those techniques to solve Poisson's equation. Okay. So, it is a similar case here, and a good estimate of the penetration depth of the electric field is something called as the Debye length, right. It is it provides a rough estimate as to how to what extent the band bending occurs, and we define this H or this thickness of the electron sheet. Okay, it is still not yet a sheet, but the thickness of this cross section of conduction to be H, which is approximately the Debye length, and the Debye length is approximately the thermal voltage divided by the electric field at the semiconductor insulator interface, but the electric field in the semiconductor at the semiconductor insulator interface. So, this is our definition of the Debye length, and that turns out to be this. Okay, so, we assign 3 parameters here, right. So, this is our equation, for the current. We know what the diffusion coefficient, because it is kT mu n by q, we will not define that any further. Q is a constant, W is a channel width, H was undefined, so we have defined that, N of 0 was undefined, so we have defined that, N of L is undefined, so we have defined that, and L is the channel length, so that is defined. So, now we have all the parameters needed to identify the current in the subthreshold region, and the current is simply the combination of all these, and it turns out to be this equation here. Very rough approximation, many things approximated here, right. Now, if you take NPO and say it is nothing but Ni square by Na, okay, and if you say that Dn is kT mu by q, you can rewrite this expression as this particular, in this particular form. Okay. Now, what is important to note is that the drain to source current does exist below threshold, and the drain to source current is dependent on the aspect ratio, is proportional to the mobility, okay, and it is exponentially dependent on the surface potential, which in turn is dependent on the gate voltage, and it is exponentially dependent on the drain to source voltage. So, it is a very characteristic nature of the current in the subthreshold region. You have an exponential dependence on the gate voltage. Okay. Now, the subthreshold current is basically the current that is the subthreshold region, right. So, if you were to draw the IDS versus VGS characteristics, so let me now exaggerate this. Okay. So, let us say below flat band the currents are all ignored, and between flat band to subthreshold we will now no longer say that the current is 0, because we now have an equation here. We know that the current is exponentially increasing, okay, it increases, and then beyond Vt the current enters the square law dependence on the voltages. Okay. So, that is the current voltage characteristics of the MOSFET. Now, in this region, okay, this region is quite significant because beyond this region, beyond Vt the MOSFET is said to be on, and below VFB the MOSFET is said to be off, okay, or in fact extending all the way till Vt the MOSFET is technically off, it does not conduct as much current as the on state. Therefore, this region between VFB and Vt is the intermediate region from the off to the on state. Therefore, the speed at which, or the current density in this region strongly determines the speed at which the MOSFET turns from off to on and on to off, and it is a very key parameter, the slopes or the time constants, or your dID by dVg if you like, is a very important parameter to estimate how quickly the MOSFET turns on. So, we need to give a better definition for this region, particularly the slopes associated with this region. Okay. And what is done, but since the current is only dependent on the surface the exponential of the surface potential, we need to do some work to define this correctly.